welcome to video 2 of WestGrid Summer School Bioinformatics session held on June 17th, 2020. My name's Phil Richmond, and we just went through a lecture where we did an introduction to next generation sequencing data and diverse data types, looked at transcriptional cis-regulatory data sets and where to find them, how to access the videos and support. In video 1, we initialized our workshop directory and copied some scripts into that directory. And in this video, video 2, we are going to go through the mapping and data conversion using BWA-MEM and SAM tools. We will also generate bigwigs for visualization with deep tools. So video 2, starting off with an overview of a basic read mapping pipeline, and then getting into the usage for these tools. We will edit the scripts and submit them to the scheduler, and then examine output files from pre-analyzed data, kind of like a cooking show. So the read mapping pipeline, at least as it's presented here in a very basic form, just has these two analysis components and a visualization component. So in the first step, we map the reads against a reference genome. So our raw data is in the FASTQ format. Our genome was in the FASTA format, but it also has been indexed. And using BWA-MEM, we will use this to generate a SAM output file. We will then use the SAM tools suite to convert that output file into a binary form, sort it, and create an index, which will allow for visualization of the sorted binary file, sorted BAM, and the index file in the integrative genomics viewer. So starting off with the first step of that pipeline, we have either single end reads or sometimes paired end reads. We refer to those as R1 and R2 respectively. In some cases we will only have the single end, so the R2 is often optional. In order to learn the BWA-MEM command while on CEDAR, again, if you have logged out by now, we can log in SSH username at cedar.computecanada.ca. Okay. Sometimes it takes a minute to think. So we are going to make sure we are in our workshop directory, scratch, Richmond P, training, June 2020. And I've been working inside the Rosie directory. So at this point, I only have these 3 workshop scripts. Now from the command line, if I want to learn more about BWA, I can type module load BWA. We're going to be 0.7.15. Now when I type BWA into the command line, it gives me the different options. So if I hadn't created an index yet, then I would need to run BWA index and give it my FASTA file. But because we already have our index, we can go ahead and just explore the BWA-MEM command. So you may notice there are quite a few options for BWA-MEM. However, today we are just going to focus on the default. So what you need just to run it as a very basic analysis method. If you do want to get into changing the different scoring options or the input and output options, then those things can be explored outside of this class, or feel free to discuss them with me more. If you hear the little footsteps walking around, that is my dog Sherlock, and he wants to play right now. Anyways, BWA-MEM, if we break down this basic usage statement, we type BWA space mem. We then provide the options. We then provide the index, and then our FASTQ for read 1, and if we have it, FASTQ for read 2. Something to note about this standard option flag is that the square brackets are indicating things that are optional, whereas the angle brackets are required options. So within our script, you can see that we've already put this together. So if we scroll down within our script, we see the first thing that it's going to do is map reads to the genome. There's a little if statement, which is useful if you're not using a workflow manager, but this if statement just says if the SAM file doesn't exist, then go ahead and create it using BWA. So again, BWA mem, the options that we are invoking in addition to the basic default parameters is we're going to use the -t options to specify the number of threads so that we can get this to multi-thread with the 8 CPUs. We are using the -m option to allow reads to have secondary mappings. And then we are also adding a read group identifier, which will be useful if using tools like GATK, Genome Analysis Toolkit, which require such read group identifier information. Now this read group identifier, this is just essentially a tab delimited string that will go at the top of the file, and then it will also tag in the individual read lines of the file such that we are keeping our ID and our sample, so we know that this is polymerase 2 heart left ventricle. If we wanted to merge these files together later, we'd always be able to pull apart which read came from which sample. I then refer to the index, which again we specified above, which will be this path here. That's the BWA index. I then refer to FASTQ R1 and FASTQ R2, which again we defined here. After downloading them, we then renamed them to be FASTQ R1 and FASTQ R2. The output SAM file that we're going to have is going to have some sequence information at the top, and then it will be tab delimited where each line is one read. So it'll go read 1 on line 1, then read 2 on line 2, read 1 on so on and so forth. So if we look at, we can actually look at an example of a SAM file. So within this directory, within our files directory, process pol2, we can go ahead and look at one of these files using the more command. And again, you can see some sequence information at the top. These are the different contigs present in the file. The information about how we actually ran our command, the BWA mem command itself, and then we get into the different read identifiers. So that's the first read, R1. You can see that this looks like it's represented twice, although this is R1 and this is R2, and it has information about where it was mapped and other information within here. If you're interested, you can look at the specifications for the SAM file format. So now we're going to go back to where we were. So just to reorient you, I'm in my training directory here, and we are going to open back up our script so we can continue looking at it. The next step here, after we have our SAM file, we will check to see if the BAM file exists, and if it doesn't, then we are going to run SAMtools. So we can look at this different SAMtools commands, module load, SAMtools. Which version am I working with here? 1.9. So I load that, and now when I type SAMtools, you can see SAMtools is actually a suite of different tools. The ones that we're going to be using include SAMtools View, so we can convert from SAM to BAM. We will also use SAMtools Sort, so we can sort our BAM file by coordinate positions in the reference genome. And then lastly, we will use SAMtools Index, so that we can index our sorted BAM file. So within the script that we actually have, SAMtools View is piped directly into SAMtools Sort, both of which are making use of the multi-threading capacity of SAMtools using the -- threads option. And after essentially this view and sort combined, I will then do SAMtools Index on the BAM file. If you need an easier breakdown of SAMtools, you can do these independently. So this is an example of using them independently. You can do SAMtools View in.sam out.bam, SAMtools Sort in.bam out.sortedBAM, and SAMtools Index, which you just apply to the sorted BAM file. The last step will be creating a bigwig from the BAM file for coverage visualization. So again, we check if we have the bigwig file, and the BAM coverage option just has -B to give it the BAM file. We want to output a bigwig format, output format bigwig. We're going to use multiple threads, and our output file will be the bigwig file. So when we finish running this script, once we essentially have our script finished, what we will do is we will submit it to the scheduler. So we can double check our script before submitting it. Do we have the correct reservation information? Did we put our email down? And did we adjust our name so that we're actually in the right working directory? And after this, we can just submit it. Everything looks good. So sbatch and then the name of the job script. Now, because I'm outside this reservation, this is actually not going to work. But during the class, this is a functional script. If you need to work outside the class, you can always change this account to be something that your Compute Canada account has access to. Now, for problem set 1, I'll introduce this before ending the video. We will be editing the scripts from the polymerase H3K27 acetylation and ATAC-seq datasets. We're going to submit them all and ensure that they can run. This will take about 1.5 hours using 8 processors, so start it now, make sure it runs without errors, and then continue working. Step 3 of the problem set. Problem 3, go to encodeproject.org, find an ATAC-seq dataset in human, create a new script. I would recommend just copying the existing one that you have and changing some different file path names, download and process the data. And then lastly, if you do have this option and you get to it, from the same website, you can find an ATAC-seq dataset in mouse or musculus, download it and map it against the mouse genome. A hint is that the BWA index for mouse genome version 38 already exists within this collated set of reference genomes from McGill. And that's it for video 2.